Hello, welcome to the next video in chapter 3 in the book by Shankar. So in this video we'll do Newton's third law. We have an example, so this example right here is pretty similar to the example in the book, but slightly different. So we'll do that one later after a couple more instructive examples. Okay, so Newton's third law you've probably heard before. For every action there's an equal and opposite reaction. Which is true, but we want to be a little bit more careful in that statement, just because it's easy to get a little confused with that statement. So let me refine that statement as follows. For every force on object A from object B, there's an equal and opposite force. OPPOS. Yeah, that's right. So what equal and opposite force means is equal in magnitude and opposite in direction. Equal in magnitude, opposite in direction. There's an equal and opposite force on object B from object A. So this refines the statement that you might have heard before, because it makes clear that a force is an interaction between two objects. And so Newton's third law is talking about the two separate objects involved in that interaction. Okay, so associated with this is that you'll never see so here there's two forces involved. Two equal and opposite forces, right? There's two forces involved in that statement. You'll never see both of these forces on the same free body diagram. So the reason for this is the free body diagram shows all of the forces acting on one object. You pick whatever system you want to analyze, that's your object. So the forces on that object come from outside that object. So if your object is object A, you're only drawing forces on object A that come from something else, object B, for example. So the Newton's third law pair for every force that you draw on your free body diagram is going to be on object B, on a free body diagram for object B. Okay, so this is one important point with that. So you'll see this summed up, this is a little too succinct, right? F12 equals minus F21. So instead of A and B, your book is calling it objects 1 and 2. And so these are actually vectors. So I kind of don't like how, this you could think of, there's a coordinate system set up where the direction is along the force, the line of force, and that's where that minus sign comes from. But really, this is a vector equation, so I would have preferred that there were vector signs on this. Okay, so now some examples. Okay, so so a lot of people don't like Newton's third law. That's a weird looking person, because it's kind of weird. I mean, imagine a person's pushing on a wall. Push on a wall. So what we're saying is that if you push on the wall is pushing back on you. So a lot of people wouldn't say that. A lot of people, if you ask someone on the street, they're not comfortable with that fact. So what's going on here is that, you have to separate the two objects involved. There's a person and a wall. So if you're pushing on the wall, what's going on is that, so what we're saying is that if you're pushing to the right on the wall, for example, so in this picture you'd be pushing to the right, then a free body diagram of the wall would have a force, your applied force, to the right. So what Newton's third law is saying is that if you drew a free body diagram for you, there's a Newton's third law pair for these. Okay. Now I didn't put a minus sign because in the free body diagram we're just putting the magnitude of these vectors. So notice how these two forces are the Newton's third law pairs. F applied, F applied. They have to be the same type of force. So this is a contact force. which means the Newton's third law pair has to also be a contact force. So you push on the wall to the right, the wall is pushing on you to the left. And you might say, there's no way the wall is pushing on me. Well, imagine you're on a skateboard, right? So you're not just on the ground. Imagine you're on a skateboard or some other, or maybe you're on ice, something without friction, something that takes the frictional force, that removes the frictional force. If you push on the wall, you can imagine that you would actually start to move away from the wall. Okay, so the reason you don't notice this in general, or if you think about actually doing this with you on the ground, there's actually a frictional force that will make up for this, which is why you don't move, even though you're pushing on the wall. And then for the wall, there are other structural forces that are keeping the wall in place, that are pushing back. You apply something on the wall, but then the wall is connected to a very strong support right here that's providing an equal and opposite. Well, I shouldn't say equal and opposite because it's not because of Newton's third law, but it's just to keep this thing in equilibrium. Okay. Example 2. Let's go back to black. Example 2. Let's say you had let's say you're pushing a block. Push a block to the right. But because there's friction, because of friction, the block is going at constant speed. So without friction, this thing would be accelerating if there was a net force to the right. But because friction, you're only pushing on it as hard as friction is pushing to the right, or sorry, friction is pushing to the left. So these forces are canceling each other, and this thing is moving at constant speed. So push block to the right. Because of friction, block moves with constant speed. Moves at constant speed. Okay. Now Shankar mentions that so that's what all of this. So read at the bottom of this page. Sorry. We are now going to put the laws to work. You have to be good at writing down the forces acting on a body. That's what all these problems are going to boil down to. Which is true. I mean, a big part of just Newton's laws is being able to draw the free body diagram and get the forces right. I mean, really, if you're having trouble with these problems, that's probably the source of this. So let's make sure we can draw a free body diagram of the block first. And then we'll be a little bit more careful and talk about all the forces acting on the block. Maybe to give myself room. Okay, so free body diagram is there's an applied force. So this is the person pushing to the right is the applied force, F applied. And then there's going to be a frictional force that's acting to the left, which is why the block isn't accelerating. So we'll label this with the lowercase f for the frictional force. So frictional force. Then there's a normal force up and the gravitational force down. So there's mg vertically downwards, the normal force vertically upwards, the applied force to the right, and the frictional force to the left. And the vertical forces are going to cancel out, and separately the horizontal forces cancel out. And so there's no acceleration. Right? So separate from the free body diagram, you could say something about the acceleration, but the acceleration is 0. Right? All of these forces are canceling out. Okay, I want to look at all of these 4 forces in the context of Newton's third law. All right. So for each of those forces, so I'm going to talk about a force on the block, force on block. There's 4 of them, which we just described in the free body diagram. I want to be specific about what the other object is involved. So the free body diagram here is the block. It's a free body diagram, all the forces acting on the block. For every one of those forces, there's another object involved. Right? So we want to be able to specify what that other object is. And then we should be able to specify, so Newton's third law says that for every one of those forces on the block, there's another force from Newton's third law. So we want to be specific about what that other force is. Right? Okay, let's fill in this table. So there's the applied force on the block. So it's assumed that something is pushing the block to the right. Let's say it's you. You're pushing on the block to the right. So the other object here is you. So if you are pushing on the block to the right, the block pushes on you to the left. Okay, maybe you don't notice this because you're on the ground and friction's holding you in place. But you know, if you're on ice and you start pushing something heavy to the right, you're going to start drifting to the left. The block is pushing back on you to the left. Okay, that's one of them. What about the frictional force? So, well, maybe frictional force is maybe the hardest one, so let's save that one. Let's be specific that the block is resting on the ground right here. You're probably most familiar with weight, right? You know that weight appears on every free body diagram, so let's study that one. So what's pulling vertically downwards on the block? So you might say the ground right here, but that's not right. It's not just the ground that's pulling down. It's the whole Earth. It requires the whole mass of the Earth to pull down on this thing. If it was just the ground in space, that's not going to provide this gravitational force. So this force depends on the whole mass of the Earth, a huge mass pulling down on it. So if the Earth is pulling down on the block is pulling up on the Earth. So the block pulls upwards on the Earth. The reason we don't notice this is that the Earth is very, very massive. So, you know, that force, even though it's equal in magnitude to the force on the block, you really don't notice it for the Earth. Okay, so the Earth pulls down on the block pulls up on the Earth. And this is a non-contact force. So the Earth doesn't need to be touching the block in order to provide that force. The block doesn't need to be touching the Earth to pull up on the Earth. Right? So again, it's the same type of force. What about the normal force? Well, the normal force, the thing that's pushing up on the block is the ground. So if the ground pushes up on the block pushes down on the ground. Block pushes down on the ground. Okay, so notice how all of these forces in this column we're not drawing on the free body diagram, right? They involve a different object. The other object, so if we drew a free body diagram for you, we would include this force, this force right here. If we were drawing a free body diagram of the Earth, we would draw this force. If we're drawing a free body diagram of the ground, and we would have to be specific about what exactly we're including from the ground, then we would include this other one. And then there's one final force, the frictional force. And maybe this isn't quite so obvious yet because we haven't talked about friction, but the other object involved is also the ground. Okay, so it's the rough surface that's actually pulling to the left on the block. Okay, so if the ground is pulling on the block to the left, the block is pulling on the ground to the right. This is probably the hardest one to think about. Block pulls on the ground to the right. So maybe that one is the hardest one to think about, but maybe it'll be clearer if you think about the block on top of a book or something. Maybe the block is on top of another block, and imagine you pull on the top block to the right. And there's friction involved between the top block and the lower one. So if that's the case, then you can imagine you're dragging the lower block. It's the frictional force that's providing that dragging force. So if you pull on this thing to the right, there's a frictional force acting to the left on the block that you're pulling on to the right. But then for the lower block, because of this equal and opposite force to the right, that lower block is dragged along with the top one. Okay. Or maybe this is maybe with two blocks that sounds confusing. Just imagine a block and maybe a piece of paper underneath. You can imagine the piece of paper could be dragged to the right. And that's because of the frictional force between the block and the paper. So if the paper is providing a frictional force to the left on the block, then the block is pulling to the right on the paper, which is why the paper is dragged along with it. Okay. So with those done, we can go back to our original problem now. So we have a block M1 and M2, two blocks, connected via a string with tension that we're calling T1. And then this rope is the one we're pulling on that'll have tension T2. And we know the value of the tension T2, which is how hard the person's pulling on the rope. And we can solve for the tension T1. Okay. There's a couple ways to do this problem. And yeah, your book talks about both these ways with its example. So I'll do both ways of solving this. Okay, so original problem, solution 1. Then we'll do a solution number 2. And neither one's better than the other one. They're just two ways of thinking about the same problem. So if you understand both of them, that's good. Okay, so we have two main objects involved, M2 and M1. So we're going to draw a free body diagram separately for each of the two objects. So we have M2. Now a free body diagram is the most important way of solving all of these problems. You really need to be able to draw a free body diagram for any object involved in your problem. That's the only way you can guarantee what's going on in your problem. And then M1 right here. Okay, so there's T2 is the tension in the second rope, pulling to the right on M2. Now there's a tension pulling to the left on M2, and it's pulling to the right on M1. So you could think of these two as being the Newton's third law pairs, actually. So if M2 is pulling to the right on M1, and M1 is pulling to the left on M2. Okay. Now, you could be a little bit careful about this and say, well, this part of the rope, like this little piece of the rope right here, there's actually like a, so that piece of the rope is pulling to the left on the left side of it, or sorry, it's pulling to the left on the right side of that rope, and it's, well, I guess what I'm saying is that this whole thing is like transmitting the force between M1 and M2. If the rope wasn't there, M1 would push directly on M2. And so the tension in the rope is just, it's sort of undiminishing, it's transferring that force undiminished if the rope is massless. So that's why we could ignore the intermediate step right here of the rope. So I guess I was explaining why could we ignore the object of the rope in the middle, right? So you could think of the rope as a third object. If the M1 is pulling to the left on the rope, then the rope is pulling to the right on M1, and then this side of the rope, it's the same thing with M2, but then these two have to cancel out. So these two have to be equal because the rope doesn't have a net force on it. If it did and it was at massless, then that would be infinite acceleration. So that's one way that you could reason that the two forces within the rope, pulling on the rope on the two sides, have to be equal. So all this is to say that the tension in the rope has to be the same everywhere on the rope. That's why T1 is the same here and here. Okay, sorry, that was a little long-winded. Now, in addition, there are gravitational forces acting on both of these things, so M1G and M2G. And then there's two normal forces. Now, I don't want to just call it N and N, because they don't have to have the same magnitude. So if you have more than one normal force, you should label the normal forces in your problem. So we have N1 and N2. Now, all the interesting stuff is happening in the horizontal direction, meaning there's no acceleration in the vertical direction. So we already know N2 has to equal M2G, and N1 has to equal M1G. Okay, so that's that component isn't terribly illuminating. But the horizontal one is. Okay, so now we're going to do the sum of the x components. So sum of the forces on M1, and we're looking at the x components, is equal to M1AX. Now, these two blocks are going to move together. Let me write this a little bigger. Sum of the forces on M1 This is equal to m1a1. But we can specify and just talk about the x direction. So we already know n1 is equal to m1g. Right? So in other words, this equation, if we look at the y components, it equals 0 on the right-hand side. So the vertical components have to cancel. So the interesting part of this is the x components of the forces is equal to m1 times the x component of the acceleration. Now I could call this ax, but there's only one acceleration in the problem. And m1 and m2 are actually moving together. So we can also say that the sum of the forces on m2, the x components, is equal to m2 times that same acceleration. So because these two blocks move together, we know that those two accelerations are the same. Okay, so some of the forces on m1, it looks like there's only, so the x components of all the forces, there's only the tension. So T1 is equal to m1a. And then on the right-hand side, we have, okay, so sorry, looking at the left again, m1, there's only a rightward force acting on it. So the acceleration we definitely know is to the right. So we're going to call this the plus x direction, and then a is positive. All right. So looking at this one, looking at m2, we definitely know that the t2 has to be bigger than t1 in order for m2 to accelerate to the right. Remember, these two have to have the same acceleration. So it's t2 minus t1. That's definitely a positive quantity, and this is m2 times the acceleration. So we're using the two separate free body diagrams. We're using F equals ma, sum of all the forces is mass times acceleration, specified to the horizontal component to get these two equations. All right. Now, let's think about what our unknowns are. Okay, so what do we know? We know the masses. We're given, well, we're at least told what m2 is in terms of m1. Our unknown is, we definitely don't know T1, right? That's what we're trying to solve for. So let me show you a trick here that's pretty common. So if you have multiple F equals ma equations from different objects, especially with problems involving tension, a lot of times you have the same tension appearing in multiple equations. So notice how T1 appears in both of these two. Okay, so T2 minus T1 is equal to M2A, and T1 is equal to M1A. So this is a common trick, we're going to solve these equations via elimination. Okay, so right now we don't know what T1 is. Eventually we want to solve for it, but right now we don't know what it is. It would be nice if we could get rid of it, if we could eliminate it. So notice how if I add the left-hand sides of the equations together and the right-hand sides of the equations together, T1 will disappear. So this minus T1 and the plus T1 will cancel each other out, and we just get T2. T2 is equal to M1 plus M2A. And we're told that M2 is equal to 4 times M1. So this is 5M1A. T2 is equal to 5M1A. Now we're told in the problem statement that we're told that T2 is equal to 20 newtons. I think 3 significant figures. We're told that T2 equals 20 newtons. So this tells us that, so if 20 newtons is equal to 5 M1A, then that means M1A is equal to, if we divide both sides by 5, we get 4.00 newtons. All right. So now if we go back to this equation, T1 is equal to M1A. T1 is equal to M1A, which is 4 newtons, 4.00 newtons. And that's exactly what we were solving for. So notice how we got rid of T1 here, just to relate T2 and M1A. And then we know what T2 is, so we could get some information about M1A, and then go back and relate it to T1 using our M1 free body diagram equation. Okay, so that's our answer. T1 is 4 newtons. So if T2 is 20 newtons, T1 is 4 newtons. All right. I mentioned I would solve it 2 different ways. So let's do solution number 2. And it's going to be, there's a lot of overlap between the 2 solutions. So original problem, solution number 2. So blocks M1 and M2 are 2 different objects, but because they move together, we can treat them as one object. Okay. Anytime you have multiple objects that are moving together, you can treat it as one object with one acceleration. So our second solution is going to involve treat M1 and M2 combined as one object. Okay, so I'll draw like a little Tetris piece for, this is M1 plus M2. M1 and M2 together. Now, T1 doesn't appear in this object. So T1 is an internal force between these two. If we're treating these 2 things as one object, T1 isn't external to the object. Remember, a free body diagram involves forces acting on that object. T1 doesn't act on that object. T1 is part of the object. Right? It's an interaction among pieces within the object. So the only external forces here, okay, so we have a weight for that's acting on both of these 2 things. So it's the total mass times g. It's a total normal force. So this is not just N1 or N2 separately. It's going to be a combined normal force. And then the only horizontal force acting on these 2 things is T2. So our Newton's second law equation, as applied to the horizontal direction, just becomes the sum of all the forces in the horizontal direction, T2, is the mass times the acceleration. And the total mass is M1 plus M2A. And here we have 20 newtons is equal to, and again, M2 is equal to 4 M1, so we can do 5 M1A. Okay, so we have that piece of information. And then after we have the combined piece, we can then look at M1 by itself. So you'll see how this is basically the same thing as our original solution, right? It's just instead of M1 and M2 as 2 separate objects, it's the combined thing and M1 as the 2 different free body diagrams. So now for this free body diagram, we have T1 is equal to M1A, and then we plug in this piece of information. See, it's basically the same thing as the other solution, right? So you might complain that this is the same exact thing. And yeah, you're right, you'd be right. So T1 is, it looks like 20 over 5, or 4 newtons. So we arrive at the same answer in a slightly different way. So the combined object, we just combine them right away, but it's combined at the level of the free body diagram. You know, this was an algebraic manipulation that led us to this equation. Whereas the other one, it's actually treating it as one object. And sometimes it's useful to do that, you know, if you don't care about the internal forces. You just care about the whole system. So, your textbook does a similar example. It talks about the contact force between blocks 3 and 2. So this F right here is not a frictional force. It's a contact force between those 2 blocks. And your book goes over the same fact that you can separate the 2 objects, you know, object block 3 and block 2 as separate objects, or you could treat them as a combined, just pretend it's one object, one block, because these 2 things move together. Yeah, so your book does contact forces and then talks about tension separately. Okay.